All right, so here I have a 3 kilogram block right here, 2 meters above the floor. So this gap between the initial position and the final position is 2 meters. I like to draw this little arrow, and I like to indicate that the initial height is 2 and that the final height is 0, so that when I plug this stuff into my energy equation, I already have some of these numbers figured out. Now, if this block moves 2 this way, it means that the block on top has to move 2 this way, right? So this guy is going to move 2 meters like this, okay? And the problem says that there's a coefficient of friction here. Coefficient of friction here is 0.5. I only give you one coefficient, so that means that's both kinetic and static coefficient of friction. We don't have to worry about it. So what happens here? Well, remember, the way to think about these problems is what would happen without friction. Without friction, this would certainly go this way because there's no force opposing it. Therefore, friction is going to be going this way. Okay? And we're going to use since I'm being asked for the final speed, or the speed just before I hit the floor, I have changes in height, I have changes in speed, and I got a friction here. I'm going to use the conservation of energy equation, which means I can solve this much faster. An alternative way to solve this, by the way, would have been to write F equals ma for both blocks, combine those two equations like we did back in the day, and find the acceleration of the system, and then I would be able to use one of the motion equations to figure out how fast this thing is. So I could have done written F equals ma twice to find my A, and then 2, I could have used motion equation to find the final velocity. But what's better is I can just do this in one step using the big energy equation, and that's much, much better. That's what we're going to do here. All right, just wanted to point that out. You could do this in other ways. Kinetic initial plus potential initial plus work non-conservative equals kinetic final plus potential final. Right away here, the system starts from rest, right? It's released from rest, which means the initial kinetic energy is for both objects. The potential energy, there are two objects. Let's treat them separately. Potential energy, got to be a little bit careful. I'm going to call this guy A. I'm going to call this guy B. So it's UA initial plus UB initial. The work done by non-conservative forces is the work done by friction, because here we have friction, but we don't have any external forces, right? And remember, non-conservative is friction plus the external. So the only one here is the work done by friction. The kinetic energy, we talked about this in the previous video. Kinetic energy, I'm going to treat it as an entire system of 1/2 of the total mass times the final velocity of the system, and this is what we're looking for. This total M here is going to be MA plus MB, which is 3 plus 4 equals 7. Okay? Plus, so we're going to treat the kinetic energy as if you had just one body, because they move together, so they have the same velocity. You're able to do that. It's just a math simplification there. And then the potential energy, I have to treat them separately because they have different heights. UA final, UB final. Cool. Let's go through it, see if anything else is 0. So the 4 kilogram certainly has a height above the floor, but it has no height relative to the table, and even more importantly, its height doesn't change. So because the floor doesn't change heights, it doesn't even matter what its height is. If it doesn't change heights, it doesn't change potential energy, so we're gonna just cancel out the potential energies. So look at UA here. Whatever number this is would be the same number here, so we can just cancel the two of them out because they have the same height. So I want to do a little thing here to sort of, so you have it on your notes. The change in height for A is 0, therefore I can eliminate both potential energies. It doesn't matter what the potential energy is, it's going to be the same in both places, so we just get rid of it, make our lives simpler. Is there a potential energy for block B? Well, in the beginning it does. It has a height, but not at the end. Okay, so this simplifies a lot, and I have just these types of energies. Continuing here, this is MB GHB initial, so that's just MGH with all the subscripts, right? Don't get lost with all the little letters. The work done by friction, this is kinetic friction because the block is sliding, so it's going to be negative FD. Okay, and I can calculate this. Friction is mu normal. Do a little side thing here. And normal in this case is mg. Because I got this block here, it's being pulled this way by tension, it's being pulled this way by kinetic friction, it's being pulled down by mg. There are no other forces in the y-axis except for normal and mg. Therefore, they have to exactly cancel, and normal equals mg. So I can write that friction is mu mg. And it's the mass of the block A, obviously, so it's a 4 kilogram. I can calculate this real quick. Friction, mu is 0.5, mass is a 4, gravity, we're going to round it as a 10. So friction is simply 20 newtons. And I'm ready to plug this in here. For now, let me just continue here. Fd half big M V final squared. Okay, I have all these numbers, so let's start plugging them in. Mass of B is right there, 3. Make sure you be very careful with the letters so you don't pick out the wrong numbers. Gravity is 10. Height of B is a 2. Friction is 20. What is the distance? So again, if you move 2 down, this block over here is moving 2 sideways. So this distance here happens to be the same as your drop because they're connected, so they have to move the same distance. So this D here is a 2. Half the combined mass is 4 plus 3 is 7. V final is what we're looking for. All right. This number is a 60. This number is a 40. 60 minus 40 equals, this is 3.5. V final squared. So V final is 20 divided by 3.5, and we take the square root of that. 20 divided by 3.5, square root of that, we get 2.4 meters per second. 2.4 meters per second. And that's the answer. Whoops. Now, one last point that I want to make here is in both of these problems, we calculated the same thing. We asked for final speed. Obviously, you could get a different question. You could have a problem where I give you the final speed, but then I ask you for the mass, right? So there's all kinds of combinations of things you can do. Even though I'm asking in both of these for the final speed, I could have given you that and taken away a different number and asked you for that different number. The process would have been almost the same thing, okay? That's it for this one. Let me know if you guys have any questions.